I'm Huang Xin. I'm from I Square R. I'm the research engineer. So I will be presenting the enhancing human-robot conversational interactions. This including the situated video Q&A and the robot-initiated exception handling dialogue system. So for the situated video Q&A, this is mostly focusing on the focusing on the research of the video Q&A, so which is using open source data sets. So for the latter, the robot initiated exception handling data system, we are using the project data to do the development and research. So first, I will talk about the video Q&A part. So previously, we have worked on the STAR challenge. So for this STAR challenge, as you can see, so it's basically a situated reasoning QA data set. So you can see, for example, in this example, what is a person do with a bottle? So the Q&A model needs to not only understand the video part, it also needs to understand the question in order to, produce the correct answer. So in this example, the person is trying to putting down a bottle. So the question is asking about what does the person do with the bottle. So we need to choose a put down based on this video Q&A. So I think what's different compared to other video Q&A dataset is this dataset also provides a hypergraph for this for different scenarios. For example, in here we can know the first of all the bottle, the person is holding a bottle. Then after that we can know the bottle is on the table. So person is no longer holding the bottle. So we can use this hypergraph as additional features to help the model to better answer the questions. Not working. So it's not working. Oh, okay. So I will talk about some related work. So first I will talk about some VQA approaches for this challenge. So basically, we can approach this situated reasoning as a simple video QA answering task. So for example, there are some existing architectures we can use. For the first one is called Clipboard, which using a single transformer to encode both video and text features. So for the video, they actually propose to use a spatial downsampling method, which is I think only using part of the video features because they are using the sparse sampling method, and then they combine together with a word embedding and using a single transformer to learn to predict the probabilities of the answers. So the second architecture we can use the UDVL kind of architecture, which I think this can be considered as a lead fusion techniques, where it's using a text encoder to encode the text first. Then after that, then we use a video encoder to encode the video, and after that, it uses a coarse encoder to encode both representations and proceed to the task-specific head, which including the captioning. If we are doing the video captioning, we can use a caption language head to do the captioning task. If we are using the prediction task, we can just put a classification head to do this different task. So another approach is we can approach it as a scene graph generation. So in this approach, basically we can generate the situation graph first, and then we can do the question answering based on the generated graph, which including the symbolic reasoning. So for example, in this paper, it's called a classification and grounding. So it's proposed a two-stage approach to first generate a scene graph. So first of all, it's trying to in the classification stage, is trying to detect the possible objects in this video by using a transformer encoder. And after that, there is another grounding stage, which tries to identify what are the time frames this object appears. For example, you can see suddenly the car is disappears. So we can know the movement of these different objects based on these situation graphs in order to further to do the downstream task like answer reasoning. So actually, our approach, we actually try to explore the two approaches for this star challenge. And for this star challenge, we are mainly using the UDVL as our backbone network. And also we compare the two different methods. One is a classification-based approach, and another is a generation-based approach. So the both models are pre-trained on the How-to-100M dataset, which is also a text video dataset, but we are only using it for the pre-trained weights. So for the visual features, we extract the S3D features from the original videos, and we pass to the video encoder. So for the text, we actually concatenate the choice with the question and pass to the text encoder. And for the classification approach, we basically apply the classification head to predict either the answer. Then we also we can use it for the scene graph prediction. So for the generation approach, we simply replace a classification head with a transformer decoder with close attention to this to the cross encoder, so that we can use this generation approach to directly decode the answer as a text. Also, we can use it to decode the action series. So first of all, we try to do the scene graph prediction. So basically, the scene graph is annotation of the video clip, which including some of the triples appearing in the video. For example, like some person is holding a bottle. This can be represented as a triple. So for this classification approach, basically we are passing a dense layer to directly decode the scene graph, because this scene graph basically is so basically we can represent as a triple. So there are three dimensions. The first is the objects. Second is the predicates, which is a total number of relations, and third dimension is objects. So we just use this a single dense network to decode the whole three dimensions into so that we can represent it as a triples. So we also evaluate the performance for this triple detection. So as we can see, even though this is not a very high performance, but still for the video scene graph generation, we think is still showing a good performance, because itself is already very challenging. So we achieve roughly 13.5% in terms of detecting the F1 score of the triples. And for the recall, we achieve 16%. We also try to do the action series predictions, because we found that the action is also very useful in terms of help for the final answer predictions. So we adapted both classification and generation model for this action series prediction. So basically for classification approach, we just we just decode all the possible actions as a different. So basically, we can define different action as a different ID. So we can use a single dense network to decode the action into basically different IDs to do the classification. So for the generation model, we try to decode the action as a so basically we are trying to decode the action series as a text so that we can find out what is a final action series for a given question and a given scenario. So we compare the two approach, and we find that the generation approach actually shows a better performance. We argue that this is because of the generation approach has a better semantic. So because the answer we represent as a text. So I think this semantic relationships between the answer with a question and the text has a I think it has a better basically it can better relate it so that we can achieve a better accuracy for the action series prediction. Also, we try to explore the answer prediction by using some of the situated reasoning result. Actually, surprisingly, we find out if we are trying to use ground truth actions in order to help predict the to help predict the answers, actually we can achieve 98.8% in terms of answer accuracy. This means I think the action series prediction is actually quite useful in terms of final answer selection. However, we found out if we are using the predicted actions, actually it's close to we're using a generation model only to just directly to predict the answers. So I think this is because we are using a separate model to decode the actions. So I think in the future we will explore more methods in order to increase action series prediction performance. So that I believe later these predicted actions will increase the final performance. Also, this is our final result for the STAR challenge. So basically, we use a generation. We basically compare the two approach and find out the generation model actually shows much better performance compared to the classification approach. So this result also is a best result in the 2022 STAR challenge leaderboard. So I think for this conclusion is I think this generative multimodal reasoning methods actually shows quite good results not only for the action prediction, but it can also be used for the scene graph generation and also the multimodal QA. So I think there are lots of potential ways where we can use the generative multimodal methods to build very interesting applications. This, of course, including our collaborative AI, where we can use these generative methods to, for example, to provide the answers based on the different questions asking about the gearbox. So we also explore the using the situation graph as additional features, and I think later we will explore more to see how we can further improve the, for example, the action prediction performance in order to lead to the increased performance in the answer selection as well. So my colleagues will, Shiwei will talk about the this exception handling system. Yeah. Shiwei.
Thanks, Huang Xin. Next, I will talk about the robot-initiated exception handling dialog system. In order to introduce the task and the data we work on, I will give some background knowledge about the gearbox assembler and disassembler. In the scenario, there is a human worker and a robot cooperating on assembling and disassembling a gearbox. A gearbox contains many components, as the picture shows, casings, bolts, hub covers, and shafts. this shows the steps in the gearbox assembly, and there are 3 main steps. Among each, there are several sub-steps. In order to finish these steps, we assume that the worker will give instructions to the robot, and the robot will need to ask help from the humans to learn basic skills. During the we also assume that the robot will communicate with the human worker in natural language through dialogues. During the operation, the robot may occur several issues, and he needs to ask help from the human worker in order to finish all these steps. So the possible scenarios with exception handling contains 2 parts. One is robot needs to ask questions when he occurs any issue in operating human interaction, and the other one is for human answer to a question asked by robot. Robot needs to understand the semantics of the human utterance. So the corresponding task contains 2 parts. The first task is robot question generation. Second one is answer semantics for robot understanding human language. The second one is related with our previous work, the intention identification to understand the human interactions, because the 2 share the similar repetition formats. According to our knowledge, we propose 7 exception types that the robot may be occurred in this assembly and this assembly, and including 6 initiated by robot and 1 interrupted by human. Currently, we target on the robot initiated exceptions. We ask the outsourcing company to write dialogues for us, and among 50 dialogues, we labeled 94 generated question and the input pairs. And the table shows the distribution of the 7 different exception types, and we can see the distribution is very uneven. So in the future, we'll do more, we'll label more data and also adapt some data augmentation method to enlarge the data set. And we also labeled 57 answer semantics for human answers. The table shows the example of the label data. For example, the human will give an instruction to a robot, please take the casing base here. But the robot doesn't have the knowledge about the casing base, which belong to the exception 4. So the robot needs to ask the question to the human, and the human will give him an answer. So the task 1, the robot question generation A to generate the question. I don't know which one is the casing base, and the human will answer the black one. In order to understand the black one, we use the red columns to give the fixed repetition of this utterance. This is ontology, including all the entities we use in the gearbox assembly. It's very domain specific. And in order to evaluation the performance of the 2 tasks, we use 4 evaluation metrics: accuracy, record 5, blue 4, and the variable F1 score. Blue 4 is the maybe most widely used in comparing 2 sequences, the generated sequence with the ground truth sequence in the translation task. So here we use it as to understand whether the generated question makes sense or not. For the task 1, the robot question generation, we set 3 input settings. The first one is only use the exception type with the previous utterance. The second one is use the labeled inputs, and the third one is combine it together. And we can see from the table that the labeled inputs as an input will generate a higher score than only use the previous utterance and the exception type. So that means the quality of the input is very important. And also as the blue score shows, because in traditionally translation task, if blue score is above 30, it means this generated sequence makes sense, is understandable, and above 40 means this is high quality, and above 50 means this quality is very good. So according to the Blue Fox score, the generated question is of good quality. And for the second task, the answer semantics understanding for the human answers. The accuracy means exact matching. The variable here means the question mark in the previous slides, the data set, to whether it can detect the ground truth variables here. Okay, that's all my presentation. Thank you.